Hello everyone. Today I will present the work called Fundamental Study of Droplets Coalescence using Lattice-Boltzmann method. This is a work that we will develop along the next months. So today I will present some details of this work and also the results that we already obtained until this moment. So I am Luiz Eduardo Czelusniak. I did this work in collaboration with Natan, Vieira, Bulgarelli. We are both postdocs, researchers. Also the other collaborators are the researcher Monte, Verde, Professor Antônio Carlos Bannwart, and Professor Marcelo Souza de Castro. So droplet coalescence is an important phenomenon related with emotion stability and also phase inversion. So if coalescence is favored, so droplets will tend to join each other and form larger droplets which can segregate from the continuous phase due to gravity effects. So we are interested in study this phenomenon and related it with the phase inversion phenomenon. And the main aspect of the droplet coalescence is the film drainage. So when two droplets reach very close to each other, there is the formation of a thin liquid film in between those droplets. And how fast this film will deplete is related with the mobility of the interface. And the interface can be immobile, can be partially mobile and fully mobile. And this mobility will affect the velocity profile of this liquid film, which will affect the time that it takes to this film being depleted and to the droplets complete the coalescence process. And this mobility is also related with the presence of surfactants or not. So it's a complex hydrodynamic phenomenon to understand, and we will apply numerical techniques to do this study and better understand this phenomenon. So the numerical tool that we will use to this study is the Lattice-Boltzmann method. So different from standard numerical techniques that uses the continuum hypothesis and solve the Navier-Stokes equations, the Lattice-Boltzmann method considers the fluid as a large group of particles, and it solves the Boltzmann equation, which describes the evolution of this system of particles. The method is very efficient in a computational way, and it can be applied to simulate complex problems such as direct numerical simulation of turbulence, which I brought an example here, and also boiling phenomenon. So the main goal of this work is to perform realistic simulations of this coalescence process, both inside a stagnant medium, in a rest fluid, and also inside channel flows, which represents better the situations that we have in our experimental facilities, where the coalescence is happening inside the flow, inside the tubes and inside pumps. So we want to reproduce this coalescence in channel flow situations. So we broke our work in three steps. The first step is the code development, where we will implement a multi-component Lattice-Boltzmann method to simulate oil and water systems. Then in a later stage we will add the effect of surfactants. After the development of the code, we will apply it in validation tests. So we will select a set of benchmark tests with analytical solutions where we can see if our code is working properly. Then we will, in the late step of our work, we will try to reproduce these real coalescence situations. So the methodology of our work, we will use the Lattice-Boltzmann method, and there are several extensions of this method to simulate multi-phase or multi-component systems. The most two popular ones are the pseudo-potential method and the free energy method. The pseudo-potential is a bottom-up approach. So it's a bottom-up because it considers the molecular interactions between particles, and then based on these molecular interactions, it's derived a force able to create these multi-phase and multi-component systems. The method is very simple to implement because the force is a very simple force to implement, but it's not straightforward to assign properties, because since the force is derived from these molecular interactions, you have to adjust the parameters of this force in order to obtain a desired surface tension, for example. And in the free energy method, is a top-down approach, so you consider not a microscopic system but a macroscopic system, and then you attribute a chemical potential to this system, and then this chemical potential that's used to create a force that will make the chemical potential be constant in equilibrium. So usually the method is less simple to implement because it involves a little bit more complex computations, but it's straightforward to assign properties. Like if you want to attribute a certain surface tension, you can do this directly. Then we implemented these both approaches. We created codes with these both approaches, and we applied it some preliminary validation tests. So these tests were the planar interface case, where it's basically two phases, like a blue phase and a red phase, separated each other by an interface with no curvature. So it's a case with no two phases and a case with no curvature. Then a droplet, a static droplet, where we can measure if the surface tension that we are trying to impose in our simulation is the same that we are measuring in the final simulation. And also we did a smooth oscillation test, where it's not a multi-phase test, like we consider that the system is an ideal gas, and then we do a perturbation in the density profile of the system, and we let the system oscillate, and then we see if this oscillation matches with the analytical solution. It's not a multi-phase or multi-component case, but we can validate the hydrodynamics of our method if it's solving the right hydrodynamics. So all these tests, we observed that in all these tests the methods provided very accurate results. And we brought here as an example the solution of the planar interface test for the free energy method. So since we are generating these different phases with a force, a continuous force, we don't have a discrete interface between the two phases. We have a continuous interface. So along the location of the domain, the density continuously change from the density of one phase to the density of the other phase, and we can control the thickness of this interface. And for the free energy, we compared these solutions, these density profiles, with the analytical solutions, and obtained very accurate results. Then, after the preliminary tests, we did the simulation of the coalescence of two droplets using both approaches. So in these snapshots at different moments of time, we have that the black line means the pseudo-potential method, and the red line means the free energy method. We can see that both lines are very close to each other, so it's difficult to distinguish one from the other. And we can see that the two methods, the two approaches, at different instants of times provided approximately the same solution, showing that there is no inconsistency between both approaches. So we are confident that using any of one of these approaches we will obtain similar results. So we observed that method performed very well in these preliminary tests, and then now in the next steps of our work we can already move to the realistic simulations of the coalescence process. So I want to thank you very much for watch this presentation. I want to thank my colleagues from Unicamp for all the collaboration, Equinor for the sponsorship for our research projects, and FAPESP for the sponsorship for my scholarship, and also for all the other institutions that collaborate with our research. Thank you very much.